2 digits become sounds, texts, images. 2 digits can contain the information for everything billions of people around the world are thinking, writing, calculating, speculating, sending and ordering, what they're releasing into a data stream that will never run dry again. This data stream imparts people's knowledge and experiences. It's an opportunity for new markets. It's a danger for authoritarian, undemocratic systems. This data stream is getting faster and wider every day. It flows beneath the oceans of the world in submarine communications cables. Submarine communications cables, yellow and black wires as thick as an arm with soles of glass. They are the global data highway. And like on any highway, it has its share of breakdowns. Then, the breakdown service is called. Jörg Pockrand is a systems technician for international submarine communications cable systems. One of these has registered a fault in the depths of the North Sea. 2 days after the error message, the Deutsche Telekom employee is in the Dutch port of Den Helder waiting for the Albatross, a marine taxi, on a cool morning in February. Pockrand's task to find and rectify the problem. According to the shipping forecast, the sea will be calm and there will only be a light breeze. That's good for Pockrand and the camera team because the jack ladder on the side of a vessel is a real challenge even in the best weather. This is the Leon Taverna, a cable ship belonging to French Telecom. It's waiting a few miles offshore. France and Germany are on the same cable. Jörg Pockrand will represent the interests of Deutsche Telekom. But first, the strict safety regulations require him to practice putting on the emergency rubber suit. Hopefully it will remain just that, practice. The Leon Taverna can move submarine communications cables, find damaged cables and repair them. 2 days are planned for this operation if the weather is agreeable, but it won't be agreeable. The vessel is named after the French electrical engineer Leon Charles Taverna, who was born in 1857. That same year, the Great Eastern was built in London. It was the largest passenger ship of its day. It was uneconomical and was converted into a cable-laying ship. It was sold by its builder, Isambard Kingdom Brunel, to a speculator. A man called Cyrus Fields had a vision of using the Great Eastern to lay a telegraph cable across the North Atlantic. After many failed attempts, the vision became reality, using what was the modern technology of the time. In 1887, the first words reached the New World through a thin wire. For the poet Stefan Zweig, it was a shining moment of humanity. The many victims have been forgotten. The first telegram through the copper wire to America cost $100. Today, the cost of an individual email is almost incalculably small. Submarine communications cables cross entire oceans. They are cheaper than satellites, cheaper and more reliable as data carriers between the continents. Jürgen Ritter is Jörg Pockmark's boss, the man whose job it is to find the problem in the cable that comes ashore here. But where exactly?
I have to disappoint you there. You can't see a cable here because there's no place where the submarine communications cable visibly comes out of the ocean. The cable is buried 3 meters deep and it runs through the dike. We've done that for security reasons to protect the cable from vandalism and sabotage.
The faulty cable connects 4 continents. It belongs to a consortium of 94 partners. Anyone with an error in their section has to look for it, starting where the cable ends, or begins.
This is a submarine communications cable endpoint. There are many sorts of cables, but I'm a fan of these. This is an endpoint that we at Deutsche Telekom run as part of the consortium. It ends here in Norden, in this building.
It's a deliberately inconspicuous building. The submarine communications cable lover likes to show visitors the object of his enthusiasm.
The exterior of this cable is very strong to protect it from mechanical damage. Inside there's a copper wire that transports the energy. It feeds the repeaters. Right in the middle you see the components that convey the information. That's the fibre optic component.
A stable interior. The consortiums register little damage. The cable customers must have a reliable connection. There is a backup connection for every submarine communications cable, but nevertheless, damage does occur.
This cable section has come into very close contact with fishing equipment, with a trawl door, which is dragged over the ocean floor by the fishing vessels, and it can get caught up in a cable like this. This is the result.
The worst-case scenario. It's rare, but when it does occur,
then that's an emergency. If an entire submarine cable fails, we have many alarms going off. We have to assess these alarms, and we have to decide relatively quickly whether we are dealing with a problem that can be fixed or whether the entire cable has failed.
If an entire cable does fail, these computers immediately switch over to backup cables. If the flow of data slows down, the location of the cause can be determined down to the precise kilometre.
There's a tear here in the fibre optic cable. We have a cable fault at kilometre 595.
The position, kilometre 595, belongs to Deutsche Telekom. In the North Sea, just before the cable branches off to Belgium, the Leon Taverna will look for the problem. The crew make their predictions.
We expect to have a classical...
The head of the operation says it'll be a classic operation. Jörg Pochrand says they may get bad weather, but then they'll have to wait. The second officer says that, thanks to the different forecasts, they know pretty well what to expect in their target area. The safety officer says they're well prepared. The technician says that, as always, they know when they're going out, but not when they're coming back. The splicer says it will take time. We'll probably have to cut the cable twice, says the youngest crew member, and the captain says they have a working plan for operations like this one, and it will all go so smoothly if they follow that. And the apprentice will be happy to get home afterwards. The southern North Sea, the target area. It's day 2. The search begins. For a needle in a haystack? This needle, or cable, is emitting a sound. It's just a matter of time before the ship's sensors locate this sound. Tension on the bridge. The German technician is waiting for a first acoustic contact with the cable. Although it's defective, it can still be located. Jörg Pochrand had a telephone call with his colleague in the German Submarine Communications Cable End Point Centre this morning, requesting a signal.
So Jörg, I'm at the PFE now. What did you want exactly? 25 Hertz? Okay. And then 100 milliampere, yeah? Okay.
PFE stands for Power Feed Equipment. The technician is feeding the cable with a certain voltage and a deep sound. Both signals are located by the ship's sensors. Using these signals, the Leon Taverna will position itself over the cable on the sea floor. In the place where the sound and the current change in an unusual way, the fault must be located. What is then supposed to happen sounds very simple.
We are going to use our ROV, our remote-controlled robot, and we'll send it down to the cable, to the place where the fault is, so it can determine the nature of the fault.
The internet is like an underground system with stations, domains, servers, cloud computing and services such as YouTube and Wikipedia. Every new station influences the entire system. It is expanding into a space now limited only by the capacity of the fibre optic cables.
Fibre optics is a gift of nature. The cables have an almost unimaginable bandwidth. Without that, we wouldn't have the internet. We wouldn't have emails, no YouTube, no Google, no broadband communication such as video conferencing. None of this would be possible.
The video conference of the next generation. The communication partner appears three-dimensionally on the screen. The chat partner from overseas seems to be sitting within touching distance in the conference room. This technology has been developed at the Heinrich-Hertz-Institut, part of Berlin's Technical University. The people here are working on the future of three-dimensional imaging, on displays with depth. The tiresome glasses will become superfluous. With our normal camera, and on your normal screen, we only show you an approximate impression. It has to be seen to be believed. It works, but the new screens will probably not be available in shops before all the existing 3D glasses have been sold. Everything that will influence the market of tomorrow is being developed here. Here, the digital technologies are tested for their suitability for everyday use. Three-dimensional images on the computer screen. Three-dimensional objects can be recognized without glasses and controlled with gestures, without a mouse or keyboard.
I'm standing in front of an autostereoscopic display. These autostereoscopic displays have to make information available for both eyes, and so they need more information, which increases the amount of bandwidth needed to deliver that information. We're also developing interactive technologies. In the future, people will need a return channel for their interactive television, and that too will require more bandwidth.
Telephone calls, movies, X-rays, share prices and video conferences all on one data stream? How can that be possible? Digitalized material is turned into data packages. These packages contain an address, and so they are sent on the data highway. The wider the highway, the more lanes it can have. The lanes correspond to the frequencies, and the cars correspond to the data packages. They contain very different passengers, emails, telephone calls, movies, data in other words. When the packages have arrived at their destination, their passengers are unloaded again. But how are more vehicles, more packages got to their destination in a certain time? The answer is being researched in this laboratory, on a test route. It is 5,000 kilometers long. 5,000 kilometers?
It doesn't look that way because we're taking advantage of a technical trick. We have a recirculating loop control here with which we can cascade the fibers in this cable to replicate several thousand kilometers here in the lab.
Loop control? The few kilometers on a reel become thousands if they are turned into a loop. The data packages are sent on several rounds through the fibre optic lanes at the speed of light. At first, yes, but over long distances the light is slowed a little.
When we transmit the light in a fibre optic cable, it goes a bit slower than it does in air. The trick is now to keep these losses on the way to a minimum. There's a theoretical limit to this, and it would be fair to say we have already reached that theoretical limit.
The University of Jena. a city that has a history of glass. We're visiting the Institute of Applied Physics. Professor Andreas Thünnemann and his graduate student, Martin Baumgartel, are open to questions, and they also have some answers. How does the light move through glass? What about a lecture? No, we prefer a practical demonstration. Data transfer normally uses light that we can't see, so for demonstration purposes, Martin Baumgartel colours a laser beam green and sends it to the opening of a glass bottle. The interface between the water and air reflects and conducts the light beam. The light enters the water and is carried along with it. The man who spends his days with the light calls this total internal reflection.
For me, light is sexy. Modern society faces a number of challenges. But, as researchers, we see that light can provide important solutions for issues of the future.
Energy, environment, medicine. Laser light is indeed a fascinating medium. This technology was first developed in Germany 40 years ago, but the Nobel Prize for modern fibre optics went to an American researcher in 2009. Maintaining the speed of light on its path through the glass fibres is the current challenge.
We are trying to understand how a light pulse spreads through a glass material. We're trying to optimize the fibre optics for the transmissions.
Coherent light is transmitted into fibres of varying quality depending on the application. The fibres for data transmission have to be particularly long. The path from scientific experiment to industrial implementation is short in Jena.
Heutzutage realisiert man die Glasfasern.
The optical fibres made today combine different glass materials. There's a glass with a high refractive index and a further glass that surrounds this glass in a cylindrical geometry.
In this furnace, a hollow glass body is filled layer by layer with gaseous quartz. Fused quartz is glass in its purest form. The result is an extremely thick fibre, the preform. In cross-section, the fibre for a submarine communications cable looks like this. The conducting glass core, red in the centre, the coat is also made of glass. A drawing tower is 40 metres tall. Right at the top, the preform is brought up to the right temperature.
We have 1930 degrees at the moment, but we need 2100.
It starts with a drop. Gravity pulls the red-hot strand downwards. The fiberglass that follows cools, and 6 stories down the drawing process will end. On the way, the fine fibre is given a protective coating. The end product, is it as thin as a hair? It's even thinner. The formerly thick glass cylinder from the top will be around 800 kilometres long at the end of the drawing process. It will have become a fibre. It is stretched yet more when it's rolled up, adding a few kilometres. Some fibres are dyed. At the end, every reel has to be checked. Does the fibre have the desired transmission capacity? Is the geometry of the fibre structure correct over the entire length of the fibre? The fibre is a perfect high-tech product. It couldn't be improved upon. Or could it?
One example from nature is the sea mouse, which has threads on its back that also conduct light.
Sea mice? We find them in the Alfred Wegener Institute on Heligoland. Dr. Franke introduces them, Aphrodite aculata.
Carl Linnaeus gave these creatures the somewhat surprising name Aphrodite after the Greek goddess of beauty, love and sexual desire. And as you can see, this animal can exude a certain glamour.
Nature usually has good reasons when it gives living beings striking qualities, regardless of whether it's to say, "Hello, here I am," or to scare others off. Is that also true for the luminous worm from the sea?
I'm inclined to exclude that possibility when it comes to the sea mouse. These animals live at considerable depths. They're almost entirely covered by sand, where they almost never come into contact with daylight. I think these luminous colors of the sea mouse are a pure epiphenomenon, that is, a side phenomenon associated with the microstructure of the threads. It probably has no biological function, at least not a primary one.
This microstructure conducts light with minimal loss. The cross-section of the threads reveals a powerful photonic crystal, know-how from nature to optimize the fiber optics.
We are currently only using a tiny proportion of this bandwidth that fiber optics gives us, that nature has given us. It has to be our goal to secure use of that bandwidth piece by piece. We're really only at the beginning. We probably still lack the imagination to conceive what lies in store for us in the next 15 years.
In the North Sea, the Leon Taverna makes a first contact with the defective cable on the afternoon of the second day. But a storm is brewing and the swell is strong. Nevertheless, Hector, the underwater robot, is being prepared.
Vitesse navire!
A cable keeps Hector connected to the ship, which supplies the robot with the necessary energy to control the cameras and tools. The underwater robot has to go along the cable all the way to the place where the requested signal from the mainland stops. The Leon Taverna is moving along the cable route, navigating very slowly and maintaining its position exactly above the robot on the sea floor, monitored by an automatic navigation system that also regulates the ship's engines. In the early hours of the night, the sensors signal the ship is getting closer to the damaged area.
The cable is evidently damaged at this location, but that doesn't mean much yet, because this is just the exterior. That's not uncommon.
It's just as well the Leon Taverna doesn't have to rely on visibility to navigate.
It's always about this electroning signal we're still receiving weekly here. If there is a real drop in a particular place, meaning it briefly disappears, then that could be the problem area we're looking for.
A cut will be made in the cable a few meters before the signal breaks off. The robot's tools get the cable out of the sand, hold it and cut it, and then bring the broken cable up. At least, that's the plan. The black and yellow cable is indeed spotted, but it keeps disappearing again under meter-high sand dunes. This animation shows the ideal scenario. A symbol for the electronic signal runs along the route to the point where it breaks off, the problem area. But the tidal currents, waves and the wind put an end to this first attempt.
Tonight's weather forecasts haven't been very good. Now we're waiting for a good current to bring our robot back up. I'm sure we'll soon be able to let the robot back down again to look for the problem.
This is going to be an expensive forced break. Twittering, blogging, emailing, Skyping. 2 billion people communicate via Facebook, 500 million keep in touch via Skype, and these figures are increasing by millions every week. The world is communicating. Humanity wants to perceive itself in a global soliloquy. Fibre optic cables need a thick skin. In the past, it was made of gutta percha, a rubber material. But today, the delicate cable interiors are protected by cross-linked plastics. We're in Nordenham at a company by the name of Norddeutsche Seekabelwerke, or NSW, which traditionally produces cables for energy and data transport above and below the water. Up to 12 fibres are bundled here into a single strand, the heart of the cable. The plant has a long history, from copper wire to broadband technology. The first telegram took almost a day to get from one continent to the other. Fibre optics are fast.
The data rate of this fibre optic cable is excellent. A cable with 12 fiberglass strands, like the one we're just making, can deliver a whole country's communication needs. A fibre optic cable can transmit the data of 1,000 CDs in a single second. Imagine how fast that really is.
To protect the bundle of fibres and supply energy to the intermediate amplifier, copper is still used in cables, but no longer in the form of wire. A copper tube surrounds the fibre bundle.
Here the fibre bundle's in the copper tube, and we're not going to say how it gets in there.
We can't show how a long copper strand becomes a tube, but we can switch our cameras back on again, where this tube and its delicate contents are wrapped in a protective coating. What makes a cable reliable for decades? That's a company secret. But there is no secret to how it's protected. The copper tube is wrapped up several times depending on the final location of the cable. The aim is to have the cable withstand undersea earthquakes and landslips for as long as possible, and it shouldn't tear if it gets caught up in fishing equipment. Although the sea cable business is booming and worldwide data traffic is increasing, there aren't many cable manufacturers. A handful share the global market, a highly competitive market.
The cable industry consists of experiences. There's no clean science for it. We manufacture our cables and modify them again. We learn from the experiences of our different projects. It's the small things that make cables special and give them their quality. If we reveal these small things, we've lost the advantage our experience has given us.
A freight ship has docked at the NSW jetty. It will be loaded with around 800 kilometres of cable. 10 repeaters have already been built into the cable. Every 100 kilometres, these steel torpedo-sized cylinders make sure the data packages are refreshed on their long route through the oceans.
We can load 20 kilometers per shift, so it takes no more than 5 days for a freight vessel to be loaded and unloaded with the cables, and then it can go back into the Mediterranean. The journey time itself is dependent on the weather, especially in the Bay of Biscay, but it'll be between 10 to 14 days.
The Taverna, day 3. In the night, the future captains practice beating against the storm, but the weather calms down, and at lunchtime the cook will produce another exciting meal for the crew. Namely,
beefsteak in garlic with potato gratin.
the galley feeds 70 people every day, with French cuisine of course. The cook has to store lots of provisions before every trip. Looking for a problem with the cables can take time. The cook tailors his menu to the crew. The sailors on the Leon Taverna are predominantly from Madagascar. The menu, with the typically opulent French number of courses, contains several exotic ingredients. Maybe it's thanks to the culinary achievements of the cook that the mood on board the Taverna is exceptionally friendly. What does such a cable repair cost? It depends on how long it takes, but it could be hundreds of thousands of euros or even millions. Cable repair costs also impact the flat rates offered by internet providers. A further recovery attempt is scheduled for the afternoon.
what we notice is that it seems that the cable is well buried, very well buried in this part.
Yeah.
So maybe we try to grip here, pick up the cable. If it works, it's okay.
After having to wait for 48 hours in the English Channel, the technicians have their sights on the cable again. Hector, the robot, is down again to grab the cable so it can be examined and fixed. The average depth of the English Channel is 100 metres. The problem with the cable was located in a place that's not very far below the hull of the Leon Taverna. It's precision work.
The depth is about 20 meters. We'll go about 60 meters. So 60 meters in this part.
Yeah.
60 meters. We move about 100 meters left. So we can pick it up to the box. Remove the box and start the joint and insert splice there. Up to you.
The internet is a powerful market. It is changing the way people deal with each other. It is changing the world. The net is a marketplace without market rules. It is expanding in an unstoppable and unregulated manner. Every rule becomes unusable long before it reaches the marketplace. The Tulare is an Italian cable-laying ship. It will expand the internet by a few kilometres with an international crew. The Greek representative of the employer, the Spanish cable-laying expert, the navigator from Italy, the German cable specialist, the project manager from Sicily, the Italian captain, and Bernhard Wieder, whose job it is to oversee the entire installation. The Tulare was chartered by NSW for this job. A cable plough will be used between the Aegean Islands. Several kilometres of cable have to be buried in the seabed with this sharp piece of steel. Its constitution was already reached months ago. The plough is the heart of this white vessel. It's placed into the water to the rear of the ship and pulled behind the vessel. The cable comes from inside the ship, and like a thread through the eye of a needle, it will be pulled through the plough and placed into the seabed. The plough tears up the seabed and inserts the cable at a maximum depth of 1 metre into the resulting furrow. Cable layers have always faced the same problem. How can the endlessly long cables be installed in the depth of the ocean without any knots or tangles? The installation technicians of the Tulare adjust the speed of the vessel precisely to the optimum speed for unrolling the cable. A look back. How is the cable prevented from snapping under its own weight? That was once the most pressing question on the Great Eastern. An answer was found for the 1,900 kilometres of cable that came out of the huge vessel in a mathematical formula that holds true to this day. After many failed attempts, the first transatlantic cable was finally successfully laid between Ireland and Newfoundland. Weeks later, the Tulare anchors off the coast of Malta. The head of the landing party, Jens Kors, and project manager Tom Schmitz inform the ship's crew about their plan for connecting the cable on land.
Shore side to seaside.
Okay.
Okay?
Okay.
Ashore, we have a small little winch, 2-ton winch. As we will float all the way in about 10 meter, 15 meter off the shore. We stop.
After we have landed the cable will be secured?
Then you will move free laying up to the plow down position, will deploy the plow and immediately go.
Marker buoys. Suspended from these, the cable is dragged to the coast. It mustn't sink to the ground. Local boats are being used because the fishermen know the sea floor. They can judge the weather and take advantage of currents. This beachment hole on the shore has space for 2 cables. Jens Kors is expecting the divers for the current connection works. They have to bring up the tow rope that's pulling the cable onto the land. The high-tech product from Nordenham is facing its first test.
Artillery, slowly, slowly. Just have a look, a little bit attention.
After a few hours, the buoys show where the cable runs. The weather remains calm and the cables are on their ideal course. Finally, the last few meters to the beachment hole are overcome. Everything is going according to plan.
A little bit higher, please, with the cable. Okay. And just bring it easy in. Easy. Just watch it that there's no king. Okay, looks good.
By the evening, Beachmaster Kors will have almost lost his voice.
Here on land it was very easy, because it was only a short distance from the waterline to the beachman hole. That's the hole where the cable will be connected to the land cable. In the beachman hole, the cable is fitted with a plate, and it's attached so it can't be pulled back out to sea.
The last stage of work in the water. The divers separate the buoys from the cable. It will sink onto the flat seabed outside the harbour. It'll only be a few metres down. Before the Tulare can set off on its 90-mile installation trip from Malta to Sicily, the measurement engineers have to give their okay. The central control room on the Tulare has sent signals. In the evening they arrive cleanly in the measuring hut on land. The Leon Taverna, day 4. Jörg Pockrand is calling his colleague from the German Sea Cable Endpoint Center Norden. The electric current in the cable has to be switched off.
Und das müsste in der Nähe von der Joint Box BJ7-2 sein. Und ihr kriegt dann bald die PSM, dass ihr die Power runternehmen müsst. Und dann nehmen wir das Kabel auf.
This plan also has to be adapted to reality. The underwater robot wasn't able to grip the cable. A sea anchor and a cutting tool are sent down.
We are just retrieving the cable, but we still have a small problem. It's buried quite deep under a sand dune at a depth of at least 1 meter or 1.5 meters.
Again and again the cable slips out of the hook. Finally it can be cut on the sea floor. It is now clamped.
If you try to bring it up, the tension increases and it could snap. That would be dangerous for the people in the front. We've closed it for that reason. Only one person can go there, and that's me.
The whole ship is used to lift the several-ton segment out of the seabed centimetre by centimetre. This will take hours. And then everything goes very quickly. Suddenly the internet has a real location, a defined error location in the World Wide Web. Not a single internet user along the 39,000 kilometre cable will notice anything at all of the work being done on the undersea cable that connects Europe to the Far East. This place now has a name: Error Location 33A. The exterior protection has been removed. This cable has a conducting copper tube as well as a protective plastic coating. Then the fibres lie bare. Two fibre optic pairs, each of them for 8 frequencies. They are connected to the fibres of a replacement cable. The technical term for this is splicing. The splicing process looks like a surgical operation. And it is one too. A room below deck is the theatre, a dust-free space isolated from the rest of the world where, what are they, precision engineers, precision electricians, in any case, specialists are working with great concentration and steady hands. The delicate fibres are welded to those of the replacement cable. For 24 hours, 2 teams of 2 people are at work. They inspect each other's work because they can't do this job on their own. After 6 hours, it's finally time for a test. The station on the mainland has sent a signal to the repaired section. After a few tense minutes, disappointment. A further problem. And now, the whole operation again?
Yes, we'll have to start again. We have to wait and see. It could be that for some reason the measurement we got was incorrect, but it looks like we'll be here for some time.
We wait this afternoon for the first measurements, and just after that, we will decide.
This measurement says there is a second problem, so they have to carry on searching. The television team then left the vessel. The defect was found 5 days later. Jörg Pockrand photographed it and sent this image for this film via the internet as an email. The problem? A shunt fault, a graze on the cable, a short circuit with the sea floor. When the first transatlantic connection broke down in the 19th century, it took 7 years before it was successfully repaired. Jörg Pockrand's excursion was over after just 14 days.